All right. Hello, everyone. Happy Friday. I can't believe it's already Friday. Wow. Well, we are excited to kick off our 2021 Southern Plains Climate Science Seminar Series, which is a joint initiative of the South Central Climate Adaptation Science Center, the NOAA's Southern Impacts Planning Program, or SCIP, and the USDA's Southern Plains Climate Hub. We really appreciate everyone participating and joining us today, especially since we had to reschedule due to the inauguration. We are absolutely thrilled to have Dr. Jason Furtado from the University of Oklahoma discussing how climate change is impacting future winter weather events. Now, before we get started, just want to take a moment and introduce myself. I'm Christian Patterson, the science translator and communication specialist here at the South Central CASC, housed at the University of Oklahoma. But I'm not the only one helping to run this show today. Cody, would you like to take a moment and introduce yourself?
Hello, you guys. I'm Cody Wen. I am an operations specialist for the South Central Climate Adaptation Science Center. And in the chat, you'll be able to find a link to our site. And there you'll also be able to find our past webinars and this webinar when it is uploaded.
Excellent. Well, before we jump into our discussion today, let's just go over a few housekeeping details. As a reminder, even though we are all probably Zoom experts by now, please keep your mic muted during the discussion so we don't interrupt our speaker. And also, like Cody just said, this is going to be recorded, or excuse me, this is being recorded, and the webinar will be available later today on our website. Lastly, we highly encourage you to ask questions at the end of the discussion. However, feel free to add them during the presentation. That way we can have some questions ready to go for our speaker when the Q&A starts. So thank you again for being here, and let's get started. Dr. Jason Furtado is an assistant professor in the School of Meteorology at the University of Oklahoma and an affiliate of the South Central CASC. Now, prior to working at OU, Dr. Furtado was a climate scientist and a subseasonal weather forecaster and consultant for Atmospheric and Environmental Research Incorporated, a private sector company out of Boston. Now, his research focuses on large-scale climate dynamics, including coupled systems, such as the stratosphere and troposphere coupling, Arctic mid-latitude connections, and El Nino dynamics and predictability, as well as interactions between the tropics and the exotropics. Dr. Furtado uses his work in several applications, including improving subseasonal to seasonal forecasts and evaluating how we understand the Earth climate system, along with its modes of climate variability and how this will change under future climate change conditions. Now, outside of research and teaching, Dr. Furtado performs outreach activities for K-12 and undergraduate students to promote STEM education and careers. He has also been featured in several media outlets for his expertise in weather and climate dynamics, including CNN, The Washington Post, and the Discovery Canada. Now, with that, I'd like to turn it over to Dr. Furtado for today's presentation. Dr. Furtado, take it away.
Hey, well, thank you very much for that great introduction, Christian. And thank you to the South Central Climate Adaptation Science Center for giving me this opportunity to talk to you today. So everyone, welcome. As was mentioned, I'm going to actually talk about today about the Arctic, the warming Arctic under climate change and how that's actually impacting what I argue is impacting our winter weather currently in the present climate and may impact it in the near to perhaps distant future as well. So this work, of course, would not be possible just alone. For this particular work, I've had several people who I've collaborated and who have helped me. So I have some people here in this image. I'd like to thank research assistants here at OU. I'm trying to get my laser pointer. There we go. So I've had two great undergraduate research assistants that have helped me with this, Bailey Jarrett and Carly Narodsky, who was actually a research and experience for undergraduate student back in 2017. Current graduate student, Ollie Millen, who is a PhD student working on subseasonal subseasonal forecasting for the central and southern Great Plains. And then 2 colleagues back east, Matthew Barlow at University of Massachusetts Lowell, and Judah Cohen, who actually works at AER, where I formerly worked. And of course, this work would not be possible without funding from the National Science Foundation and also the NOAA Modeling Analysis Predictions and Programs program out of NOAA. Okay, so let's get started. So as we probably already know, our climate is warming, and it's been warming over time. So what I have here is an animation created by NASA. It's temperature departures from the mean, which is taken from 1951 to 1980. And it's been averaged over 5 years. I'll let this loop around again. But every 5 years, taking what the average temperature anomaly was during that period. And so we can see that starting from the late 1800s until now, blue colors are colder than average and red is warmer. You know, the first thing we're going to see is that obviously with time, those blues are suddenly becoming red, right? And this is our changing climate. This is our warming climate, which now we're pretty much 100% certain that this is from anthropogenic climate change. But what I want you to notice is towards the later part of the panels, and again, this will go again, as we start to warm, especially focus on the northern hemisphere, and then also at the very high latitudes. The pattern of warming we talk about a lot being on the average over the globe it's warming, but different spots are warming at different rates. And this is especially true across the northern hemisphere, where we see warming really starting to intensify here by the late 1970s. And then you'll see that warming grows really high as we get to the highest latitudes. So the highest latitudes here in the Arctic are experiencing warming rates that are much faster, much bigger than other latitudes. And that's an important consequence of climate change. And in fact, that's something we call Arctic amplification. So the idea behind Arctic amplification is that the Arctic, although the entire globe is warming, the Arctic region in particular is warming at rates almost double or even more than other parts of the globe. To illustrate that, on the right here, what I have is a graphic of the trend in temperature between 1997 and 2017, taken from a paper by Zhang and Peng in 2018. And the reds here again are, this is a trend, so it's Celsius or Kelvin per decade. And so you can see that, of course, here in the ring, sort of poleward of 60 degrees, we've had positive trends going on in that latter part of the 20th century and early 21st century. That's Arctic amplification. Now, what's interesting about this, of course, is that if you look outside of there, you can see those blues. Those are negative temperature trends. So that's kind of strange. Oh, by the way, I should say this is winter time only, not over the whole entire year. So Arctic amplification is really causing large changes at the highest latitudes, but during the winter months at least, something strange is happening at mid-latitudes. Now, why does the Arctic warming so quickly? Well, it has to do with a lot of different factors. One of the factors has to be that as the climate warms, we're losing a lot more sea ice and snow cover at the highest latitudes. Those are reflective surfaces for the Earth. If you start losing a lot of that, then what's going to happen is you'll have more sunlight that can be actually absorbed, and that can cause more warming to happen. Of course, as it warms more, you lose more sea ice and more snow, and that, of course, causes more sunlight to be absorbed. And so then you'll have further warming. And so you set up this loop going on with that. In addition, because the entire globe is warming, we're also advecting or transporting more warmer air and also waters in the ocean, because now we have more open ocean from the sea ice loss, into the Arctic, causing it to warm even further. And then we're also changing cloudiness. So in the Arctic, we're developing much more low cloud, so lower at the surface. And that can actually, what it does is sort of acts like a blanket, and it traps heat from escaping from the surface, causing even further warming. So for all of these reasons, the Arctic is a special place that is experiencing this rapid warming across our planet. To illustrate the sea ice loss, I have this animation here from again, NASA. Let's see if it's going to start. Sorry. Don't see it starting. Okay. So that's okay. But the point is that we are losing tremendous sea ice over the Arctic with time. We're losing a lot of sea ice over there, and that's also helping to amplify the Arctic warming. Okay, so the Arctic is warming up, especially during the winter months. What does that have to do with the mid-latitudes, or the, areas where we live, between 30 and 60 degrees north? Well, there's a review paper that I was actually a co-author on back in 2014. And we sort of looked at all these different connections that are going on. So here we have the Arctic amplification, which is a result of our global climate change for the reasons that I just talked about. Well, that Arctic amplification causes changes in our cryosphere, less ice, less snow. Less ice, less snow. The curious thing, of course, that I'm not going to talk about in this talk, but actually during the autumn, we've actually been seeing some increases in snow cover happening. And that has to do with more moisture being transported from an open Arctic. But the idea here is that we've been losing a lot of sea ice. The Arctic is warming, and that's going to have an effect on the rest of the hemisphere. Why? Well, within the northern hemisphere, temperature decreases as we go to the north. So it gets colder as you go further north. That temperature change, or that temperature gradient, helps to form what we call the jet stream. And that's the river of air that goes around the hemisphere that brings about storms. It also divides up the cold versus warm. Well, if we start warming at the highest places faster than what we're warming at the lower places, that difference in temperature that's important for the jet stream is going to become less, because the higher latitudes are getting warmer faster than the lower latitudes. So that's going to affect the jet stream. It's going to affect where the jet stream goes. And of course, if the jet stream changes, then that's going to affect where storms go, and that'll affect how temperature patterns are going to evolve. And then we have this one right here, the polar vortex. And let me introduce the polar vortex for those of you that have not been familiar. It's been a lot in our media and out there, but I just want to make everyone get on the same page about what I mean by the polar vortex and how it's related to the jet stream. So the polar vortex is a feature of our climate system. It's there, absent of any climate change, it is there. And the reason it develops is that during the winter months in the Arctic regions, it gets dark and it gets cold. And so without sunlight coming in, you have the air, the atmosphere throughout the column can cool very quickly. When you cool the column very quickly, that actually causes that causes pressures to start to lower. Once that starts to happen, you start to get this bowl effect happening, where you have sort of dipping pressures at the highest latitudes and higher pressures around it. And so that gradient actually forms wind to start circulating around, and you actually get this counterclockwise circulation in the northern hemisphere, way up in the atmosphere. We're talking about getting up to almost about 30 kilometers now. That spins up there during polar night, during our winter. That has impacts on the jet stream below it. So the jet stream is in the layer below in the troposphere, but the two talk to each other. And so you can think about this as being a three-dimensional structure, where you have a turning cyclone here, and then the jet stream at the lower levels spinning around it as well. When this is a strong or stable polar vortex, it's sort of like the ice skater when they bring their arms in, everything starts spinning around very tightly. The cold air gets contained up in the Arctic. Now, there are cases where the polar vortex weakens, and that's shown in the right picture here. When the polar vortex starts to weaken, that's this circulation. You can think about it as it starts to wobble, it starts to lose speed. And what that happens is then everything starts to relax. And in this picture, it's shown here, the jet stream you see starts to move southward because we're relaxing the circulation. And it also starts to develop these waves within the jet stream. And these waves, remember, the jet stream is dividing up the cold versus the warmer air. So these dips, or what we call troughs, are where the cold air is going to come down into mid-latitudes. These sort of what we call ridges, or sort of the jet stream moving northward, is where warm air can poke upward. And when you get these wavy jet streams, this is how storms are going to form. This is, relatively stable, nothing really happens. This is how you develop your big storms, your big cold air outbreaks that dive into the eastern US or into Europe. And what's interesting is actually we're undergoing right now a very weak polar vortex episode. So this is an image from satellite imagery. So the milky white image here, this is from NOAA, is that polar vortex, and you can see it swirling around here. The image starts in December and goes through the beginning of January. And you can see that through December, we had a very coherent circulation, but then towards the end of the month in early January, you can see it starting to split apart. You can see the vortex sort of being sheared and sort of forming two different vortices on the side there. And so this is an episode of one of those weak polar vortex, and that's sort of why weather recently has been getting a little kind of crazy across the whole hemisphere, and probably will continue over the next month or so. And of course, I don't have to tell you, but if you've been looking at the media over the past few winters, the polar vortex is everywhere, right? Polar vortex, extreme weather, beast from the east. My favorite here is life-threatening Arctic blast to freeze nearly 200 million as polar vortex attacks the United States, right? So, you know, if it's not the Godzilla El Nino, it's the attack of the polar vortex that's going to take us. And so this has really gotten hyped up recently. And so that then begs the question, well, how come are we just talking about it more because we have more social media and people are noticing, or is something really happening here that we should be paying attention to? And so what I want to focus my talk on today is really this link here in this sort of flow chart, is this idea that Arctic amplification is changing the jet stream via changes in that polar vortex that are then affecting our weather here in the middle latitudes. And I want to present to you some evidence of that happening. So the three research questions that I'm going to be attacking today are as follows. Number one, what are the recent trends in Northern Hemisphere mid-latitude winters? And are they coherent with this idea about Arctic amplification and a weakening polar vortex? Number two, how do the latest state-of-the-art climate models capture those trends? Are those climate models telling us those same trends that should be happening currently? And then what do those climate models then say that what's going to happen in the future? What are the future polar vortex trends going to be, and how is that going to affect our winter weather? So the first part is I just want to take a look at some observational data about what the recent winter climate trends have been across the Northern Hemisphere. So this plot here is a trend of December, January, and February averaged temperatures from 1960 to 2018, and taking the linear trend of those temperatures. And so the reds here, the color bar was blocked by the video, by the gallery thing, but this color bar here is in degrees Celsius per 10 years. So this is a change in temperature for every 10 years. And so you can see that from 1960 to 2018, everywhere has been getting warmer over that whole period, as you can see. On the left here is basically what we did was we took this trend and we averaged it across every latitude belt, and we plotted it here. And so you can see that at every latitude, it's getting warmer per year, and especially the trend is ramping up as we head poleward of 60 degrees. That's Arctic amplification. Well, we know, and again, I apologize for the movie not working, but since the 1990s, sea ice has taken a tremendous downward turn in the Arctic. And so if we start looking at the 1990s onward, what does the trend show? Well, this is the same plot, but now the trend that I've started is in 1990 rather than 1960. And so what you can see here is that, again, we're seeing rapid intensification at the high latitudes, but here in the middle latitudes, we're seeing cooling, and there's actually a slight negative here throughout the northern central plains as well. Again, if we average over the latitudes, you can see that cooling happening, right? Where the trends on the average have dipped way down to 0 or slightly below 0, but have accelerated at the highest latitudes. So the idea is that over the last, say, 3 decades or so, neutral to negative temperature trends have existed in parts of North America and Eurasia during our winters. In other words, winters are not getting warmer over the last 3 decades like you might expect during climate change, but they've actually been staying the same or slightly colder. If we focus in on the southern plains in particular, this is the temperature trend. So again, this is the average temperature over December through February across the southern plains since 1990. And you can see the trend is essentially zero. So there's been almost no warming of our winters over the last 30 years or 28 to 30 years. There's a lot of variations for sure. Here's the cold winter of 2009-10, but there has not been tremendous warming happening during this time. And if you look at other things going on over the last few decades, winter weather has been going extreme. So right here on the left here is an image from Lorimer et al. In 2014, where they were looking at the top 100 snowstorms since 1900 per region, and then plotting out which decade did that occur. So they took the whole entire record. I think they went through 2013, I think in this paper, or 12. They took the entire record, counted the top 100 snowstorms, and then just made a bar plot of when they occurred per decade. And you can see some interesting things. So again, under climate change, you might expect that most of the snowstorms would have happened earlier in the period, but actually that's not the case. The trend is extremely significant here in the northern plains and upper Midwest, where we've seen that several of the top 100 snowstorms have actually happened over the last 30 to 40 years. Oklahoma and Texas would be in the south region, which is this red, and you can see that although there was fairly steady and maybe a decline here, there's actually been an increase that happened during the 2000s. In the northeastern United States, the number of impactful snowstorms that have hit the region, and this is determined by this index called Nessus, which is developed to determine impact based on snowfall and total area extent and things like that. But you can see that the most impactful snowstorms that have increased almost threefold over the last decade or so. So winter weather is becoming more extreme. And so why are we seeing these trends? Well, again, my working hypothesis is that it's because we're seeing changes in that polar vortex in that diagram I showed you. And because the polar vortex is important for controlling the jet stream and controlling the storms, we need to understand what's happening with the polar vortex in order to get an idea of why our winters have become either not warming or even colder in some parts, especially across Asia. So how does Arctic amplification affect the polar vortex? Well, let's go through sort of step through it. So number one is, as you get the high latitude warming happening, you're bringing in much warmer air into that region. You're causing more storms, and that actually causes more heat, not just at the lower levels, but also as you go through the column, as you go into the stratosphere, you can actually transport or flux more heat into that polar vortex over the highest latitudes. Now, remember, the polar vortex is this very stable thing that just wants to spin. Once you start introducing heating in there, now you're kind of messing things up, right? And the polar vortex is going to start to wobble. It starts to get disturbed by these injections of this heat. Well, once you start to warm that'll start to weaken. And that's the idea of sort of that ice skater taking their arms apart and everything starts to relax. And so that jet stream that was once tight up here will start to settle southward and start to build more waves. And then once you get that entire thing weakening again, it'll become wavier and you'll get these cold air outbreaks that start to happen. So then the question has to be, has the polar vortex been weakening over the last 3 decades? Well, the answer is yes. And so what I'm showing here are, again, this is trends. So it's in meters per decade. And these are the average, the height at 50 millibars. So we're talking about up into the stratosphere. And this is the trend in the height. So low heights would be where the polar vortex is. So if the trend was negative, that would mean that the heights were lowering with time. That would be like the bowl deepening, and that would be the vortex spinning faster. Higher, if it's a positive trend, that means the heights are being raised. And so the bowl is not so much a bowl, it's becoming shallower, i.e. the vortex is weakening. And you can see that over the last 30 years, over the Arctic, that we've been seeing some rather impressive, almost 90 meter per decade changes. And that's actually significant. That's what the stippling means. It's a significant trend. We've seen a little bit of lowering happening over Asia and a tiny bit over North America. And so this is an idea that perhaps the polar vortex is not only weakening, but perhaps the mean area is shifting over towards Asia. If we look at this heat flux that I'm talking about, and so that's what this quantity is, we call it a wave activity flux, but you can think about an idea of how much heat is being fluxed into the polar stratosphere. And again, this is a trend, so this is how much more per decade. And you can see that over Northeast Asia and Siberia and across the Gulf of Alaska, we're seeing significant increases in heat flux. And actually, this is an area that's actually really important in climatology to sort of take heat and transport it poleward. So if we're taking a climatologically favorable hotspot already and we're adding more to it, then that makes sense that the vortex should start to weaken because we're putting more anomalous heating into the vortex in those favorable regions. If we look further down, this is now in the middle troposphere. This is 500 hectopascals. So we're talking about somewhere around 5 kilometers or so above the surface. These are the trends again in these heights. And so again, positive means raising or more ridges, more higher pressure. And excuse me, higher pressure, not more higher pressure. And then the blues are where it's lowering. And you can see that over the Arctic, we're seeing height starting to rise, which makes sense because it's starting to warm. As you warm a column of air, it should start to expand and the height should start to increase. And then we're seeing some lowering happening across North America, across Asia, and across Europe. Now, this is really interesting. The other area too is here towards Alaska, where we're seeing anomalous height rises over Alaska as well. Now, all of these things are consistent with the weakening polar vortex. We're getting a wavier jet stream, right? So think about the jet, if it's sort of following where these are going, remember these ridges are where the jet goes up and these blues are where they're going to come down. So things are getting wavier and we're fluxing more heat. All of this is consistent with the hypothesis that I presented to you. If we look specifically at the plains now, these trends that we're seeing, this is the same image here, is actually the favorable pattern that we would want for big cold air outbreaks to happen across the US Great Plains. And this is some work that's being done by my PhD student, Ollie Millen. So we've been looking at, sort of separate from this, what synoptic patterns are important for bringing cold air outbreaks, and cold air outbreaks are 5 or more winter days where the daily mean temperature falls below the 25th percentile across the plains. What's the favorable pattern for that to happen? And if you look at the data since 1950, this is the favorable pattern. So these are departures from the average of the 500 millibar surface. And you can see that the favorable pattern is to have higher heights over Alaska, or higher than normal heights over Alaska, and lower than normal heights over the northern US. And that's pretty much what this trend is showing us. So we would anticipate that cold air outbreaks across the plains probably have been increasing and leading to that negative or neutral wintertime trend. And if you look at the frequency of plains cold air outbreaks by decade, since the 1950s, you can certainly see, I mean, we had a lot of them back in the 50s and the 60s, 70s, and 80s, but there's been an increase in the number that have been happening since the 1990s, all consistent with this trend. So again, this trend is consistent. It's the vortex changing, the jet stream below changing, and creating a more favorable pattern for these anomalous or extreme winter weather patterns. So the next thing I just want to bring up are just a little bit more of these diagnostics of how we measure the jet stream. And there's 3 main things that I want to go over. One is what I call the polar cap height. So what this is I'll go back to this image to illustrate. We basically draw a circle around 60 degrees north, and we take the average of what the height field is at that over that entire circle, so poleward of 60 degrees north, and we take what the average height value is, and that gives us a measure of sort of the strength. So again, if the heights are increasing, that would mean the vortex is weakening. We want the bowl, we want low heights, not high heights. The next is going to be the size, which is a vortex area. And the third is going to be the centroid latitude. So think of the vortex as an ellipse. Where is the center of that going to be? There's a great website, by the way, if you're very interested, stratoobserve.com, run by Zach Lawrence, who is now at NOAA in Boulder. And he does these diagnostics on the models every single day. And so just to illustrate, you know, this is the latest from the weather models, sort of showing you where the vortex is, and the centers are these different dots. And he does it at different heights throughout the column here. Okay, so what's been happening with the vortex in these 3 measures? Well, the polar cap height, that's our strength measure. You can see that the heights have been increasing over time. since 1980 and especially since 1990. That's consistent. The trend up means the vortex is weakening. The area of the vortex, so the total inside that ellipse, has been decreasing with time. And you can see that here, the downward trend. So not only has the vortex been weakening, but it's also been shrinking. And the average centroid latitude, so where is the center on average? And then again, these are winter averages. Of course, this varies by day, but over the average, where is the average center of the vortex been with time? Well, you can see that with time since the 1980s, that the vortex has been shifted further southward. The degree has changed by about 0.4 degrees per decade. So we're getting a shifted polar vortex that's smaller and weaker with time. So again, quick summary of this part. Number one is parts of the Northern Hemisphere mid-latitudes have experienced cooler and more extreme winters over the last 3 decades. The polar vortex weakening trends that I've showed you, the movement off the pole and the weakening, they're consistent with that Arctic amplification flow chart I showed you. Is it caused by it? I can't just tell you that from this right now. I'll get to that at the end, but it's consistent with the theory. And these shifts are inducing that anomalous jet stream conditions and more extreme weather, the more waviness and those more cold air outbreaks and more snowstorms that we've been seeing across the mid-latitudes. The next part that I want to talk about is, do the latest climate models capture these trends? So we've taken a look at all this in observations, but now are the climate models that we run, have they been capturing the same trend? Are they capturing Arctic amplification? And if so, are they also capturing this change in the polar vortex that's been affecting our winters? So what I'm going to do is, I looked at 7 models, climate models. These are the names of the climate models, and they've been taken from this CMIP6 archive. So this is a collection of climate models being run for the Intergovernmental Panel on Climate Change for their next report. This is the next state of models that are being run and analyzed. So these are sort of the latest, greatest climate models out there. And I just chose these because these had the data that I needed, no particular special reason for choosing these necessarily. I'm going to be looking at, for this part, what's called the historical experiment. And what that is they take the models and they actually put into the models the actual solar forcing that happened, volcanoes, aerosols, greenhouse gases, land use changes. And they put that in, they start in like the 1800s and run it through till about 2011 or 2012. So the model has all the general forcing. It doesn't have the actual weather that happened. And in fact, we're not really interested in trying to match weather to weather that happens. So we never expect that the climate model will actually predict that in 1997 there was a big El Nino event. But it should capture the overall trends of these forcings and what they're causing to happen to our climate system. So the trends should be apparent, but not necessarily the actual weather. Okay, so the first question is, are the models getting Arctic amplification? This idea that the Arctic warms much faster. And the simple answer to that is not really. So what I've done is, on the left is, this is December, January, and February. This is the average temperatures per latitude. So I've averaged over all the latitude band, so averaging across all longitudes, and also as a function of pressure. Okay, and I've taken the trend of that from 1980 to 2018. And so you can see these darker colors at the surface, that's Arctic amplification, right? These darker colors happening at the high latitudes versus the not so strong warming happening in the middle latitudes. And also you can see this very strong warming happening in the polar stratosphere, the weakening of the polar vortex. It's getting warmer there. The models have a little bit of a hint at the surface about this Arctic amplification, although the trends are nowhere near the levels that we're seeing within the observational record or reanalysis, but almost nothing in the stratosphere. They have almost no changes happening in the polar vortex. So this is our first clue that the models are not getting the right, they're not responding correctly to the changes that are happening in our climate system at this period of time, especially have to do with Arctic amplification. And if we go into the models and look at that polar cap height again, you can see that, so each of these lines here represent a different model. This is December, January, February averaged. polar cap height. Remember, that's the heights averaged from 60 to 90 degrees north. And this is at the 10 millibar level, or about 30 to 32 kilometers above the surface. And you can see that with time, if you look down here in the legends, I've actually put what the trends are per decade. You can see that the trends are actually negative. So remember, positive trends that we saw in observations say the vortex is weakening. A negative trend is actually the opposite. It means that the models actually predict that the vortex should strengthen with time, not weaken with time. So they already have kind of the wrong trend going on here. Same thing with latitude. So if you look at the centroid latitude, very small changes. And in fact, some of them are actually positive changes, meaning the vortex is not only getting stronger, but staying more towards the pole than what we observe. So the models have a very stable and strengthening vortex over the last 3 to 4 decades, which is contrary to what we have. But actually, this is very consistent with other climate models that they basically poorly perform on how the polar vortex behaves. And if we look in space, what the spatial trends are, the spatial trends, again, on the left, this is what I showed you earlier, the trend in the 50 millibar surface, that weakening happening here of the higher heights. But you can see in the models, this is the ensemble mean. So this is taking all those models and averaging their trends together. You can see again that all the models actually show a strengthening polar vortex at the highest latitude. So the trend is negative, the bowl is getting deeper, we're getting a stronger polar vortex. So why are the models doing this, right? So one idea is, again, what I showed you, Arctic amplification is not being done or simulated correctly, and especially Arctic sea ice loss. So models are notorious for actually not predicting the correct rate of sea ice loss that we've been observing. Models are also deficient in how the stratosphere, troposphere, how the stratosphere talks to the troposphere. So this idea that if I change the polar vortex here, that I'll change the jet stream further below it, the models are actually do not capture that very well. And I've done a lot of work on this with CMIP, with the previous version, CMIP 5, some other models, and also this paper by Daniela Demayasin et al. That we actually looked at a whole slew of operational forecasting models to show that they also do not do very well in predicting these things. The other possibility, though, is that maybe what we observed over the last 30 years is what we call natural variability. Now, that's not to say climate change. I'm not saying climate change is natural variability, but within the climate system, we have our own variability that happens, and the polar vortex is no stranger to that. The polar vortex has its own periods where sometimes it may get stronger, sometimes it may get weaker with time. And so if that were to happen over this same period, maybe it's not the forcing that's making it happen. Maybe it's actually just that the vortex is actually just in a cycle that makes it weaken with time. And so we don't expect that the models would necessarily capture that. Okay, so that's sort of the model. Oh, sorry, window popped up there. So my hypothesis is not just number one, but also I've done a lot of work on number two, and I actually do think that there's a big component of this where the models are actually deficient in this coupling dynamics. And I'm actually going to skip over the next 2 slides for the interest of time, but we did look at this and basically find that the models are simulating the wrong interactions happening between the stratosphere and troposphere. So this is something very particular that it's not necessarily from the climate change perspective, but there's something wrong in the models themselves with how the stratosphere and troposphere talk to each other. So again, I'm just going to skip these next 2 slides and go ahead to the last part. So we took a look at what the trends have been in the observational record. We took a look at what the models did and basically didn't show. And now let's take a quick look at what the models say should happen in the future for climate change, to the polar vortex due to climate change. So now what I've done is I should preface this. So now what I've done is I've taken, this is another experiment from that same model archive. It's a scenario, SSP 585, sounds kind of like some Star Wars robot or something, but what it is essentially it's a scenario where we run things into the future. And this is equivalent for those of you that might have done some work with the previous models. This is pretty much equivalent to that representative concentration pathway RCP 8.5. And so what this is saying is that by the end of the century, we will basically have an added impact on our climate system of somewhere around 8.5 watts per square meter. Currently, it's somewhere around 2.3 or 2.4, or at least it was back in 2010-11. But this is the idea with that. So this is like an extreme scenario. In the plainest of terms, you can think about it as sort of like a business as usual, just carbon, everyone's just doing what they want to do and emitting carbon, and things are increasing. So in this scenario, what happens to the polar vortex? So I'm just going to show two plots here. First is the size. So what's going to happen with the size of the polar vortex with time? And most models predict that from the late part of the century, that the vortex will shrink considerably with time. Some of them have some quite dramatic, the CAN ESM5 has quite a dramatic shrinking of the polar vortex with time. If you look at the trends, these are those spatial trends again. So again, at 50 millibars, what are the height trends? And I've broken it down now into the period 2015 to 2050, and then the period 2051 to 2100. So sort of like next few decades and then the end of the century. Over the next few decades, the trend is a little muddled. So you can see here, it's quite weak. Looks like that there's something trying to happen here towards the Alaska, Northeast Siberia region. But remember, this is an ensemble mean, so this is averaging all of them together. So basically what this means is that the models are very variable. They don't really know what's going to happen. There's a lot of variability with time. But by the end of the century, we do see that although the heights are all positive, we do see an inclination that the heights will start to shift, or the polar vortex will start to shift more towards the Asian region. And this is actually consistent with work done by Mitchell et al. In 2013 for the previous version, the CMIP5 models. So let me just wrap up as we transition to questions and give you sort of the main conclusions of this work. So are recent wintertime weather trends in the Northern Hemisphere consistent with Arctic amplification theory? I would say yes, that they are consistent. However, I can't tell you that that's the cause. And the reason is, number one, I just have the data to show you. But number two is actually people have been looking at this over the last 5 to 6 years. And there's been a few papers come out, Barnes and Screen in 2015, and especially this new paper, Blackport and Screen in 2020, where they basically have gone into the models, looked at the data, and they don't see evidence that even when you put low sea ice and warming in the Arctic, the model does not cause the jet stream to change. Now, is that because the model is just wrong? Or is it because something else is happening in the climate system? And so the idea is that we really cannot rule out any what we call internal or natural variability happening within the vortex. And this is also something that I've been looking at within the same data set. The latest models do not simulate Arctic amplification well, and also poorly simulate our observed wintertime trends, especially associated with polar vortex dynamics. So they're not getting that consistency. And the winters for our near future, I think, are going to be highly variable. That polar vortex is going to continue to weaken. So I think we will start to see trends where we start to still have more extreme weather. But of course, the reservoir for cold air is going to start to go away as the Arctic starts to warm. So cold air outbreaks, even in the future, will become less cold. And that shift that we saw happening towards Northeast Asia by the end of the century. So the polar vortex is sort of on the demise, at least according to the models. So I'm going to stop there. I have my contact info on my website. And also, if you'd like to follow me on Twitter, my Twitter handle is @WXJAY, where I talk a lot about climate. I talk about subseasonal weather and throw in a little bit of sports and news of the day, but happy to have you follow me there. And I'll stop there and turn it over back to ask if there's any questions.